called the Factorio learning environment. I myself was like very excited about this because like I'm also like a huge like Factorio player. Like last year, I spent like the majority of my Christmas break playing Factorio. But like more seriously, like I think the reason why I think this should be interesting to a lot of people on the server is because like I think Factorio is like an extremely interesting like eval for agents, and I think like Jack will be talking more about this. And I think if you want like something like meaty and hard, and like you're trying to think about like what are important problems that are worth accelerating that aren't like really in the mainstream, you should talk more with Jack. So please, yeah, without further ado, please go ahead.
Brilliant. Thanks a lot, Mark. It's a real pleasure to be on the show. So about 18 months ago, me and a friend realized that we could hot load little bits of Lua scripts into a Factorio node and use that as a method to effectively get agents to play the game. Now, obviously, this was a Friday night, and looking at my watch, I kind of realized, hey, if we really get our act together, we can probably finish this thing by Monday morning. It's been about 18 months since that day, and it's got to the point where I can't even play this game anymore. It's become too much like work. But I'm pretty excited to talk a bit about what we've been working on. So, kind of by way of initial motivation, there's a bit of a problem in how we measure agents. Historically, we create a benchmark. It would be good for a few years, and then the progression in agent competency would saturate that benchmark, at which point you couldn't differentiate agents anymore. That benchmark effectively became dead. Now, even with more recent attempts to make harder and harder and even superhuman benchmarks, like in the case of humanity's last exam, and I guess the rather presumptuously named ArcAGI2, it doesn't look like that trend is slowing down. In fact, it looks like it's speeding up. By current projections, it seems that humanity's last exam, ArcAGI2, and probably a bunch of these other new benchmarks are not going to be that useful in about 12 months. And at the same time, we see the length of time or the time horizon of tasks that models can complete is doubling every 6.6 months. So historically, you might have a task like SWE-bench, which you could complete. You could complete a task in maybe a few minutes. Now, at this point, agents are about the 1 hour mark. So about 50% of the time, state-of-the-art models are able to complete tasks that are 1 hour. And every 6.6 months, this is doubling. So this really motivates having a new class of environments which span into the ultra-long horizon. Tasks where an agent might be expected to spend hundreds of hours and potentially tens of thousands of steps or tens of thousands of tool calls to achieve the outcome, to get to the end. So we basically need, therefore, a new set of environments that can resist saturation over ultra-long time horizons. And Factorio is quite a good candidate for such an environment. Now, what I think what we're looking for here is we want environments that are unbounded, i.e., they can't be completed, they can't really be saturated. There's like an unlimited performance ceiling. Factorio does actually, fits this bill. It needs to be procedural, so the priors of a model that have been picked up during pre-training can't really, the model can't memorize solutions and just spit them out. You want to remove the knowledge component from the intelligence component to have a meaningful benchmark in measuring model, intelligence, I suppose. You want something that's long horizon that tracks with that meter time horizon chart that I just had on screen. You want something that's consequential, where you have to make a long series of very accurate decisions in order to get to the end. And you want something that's open-ended, such that there are many different ways of achieving a goal. One example that the meter people were talking about were, launch a startup as one of the goals that they might expect models to do in the next few years. Now, obviously, there's no recipe for starting a startup. I mean, you have to do a great deal of exploration and goal setting, and there's probably dozens of ways you can get there. But what I hear from talking to my startup friends is that, there's a couple of things that you need to do when starting a startup. You need to make decisions really fast, and you need to make every decision you need to make has to be slightly above average, because you get this really nice compounding effect over extremely long horizons. So, as you all know, this is Factorio. It's the highest rated game ever on Steam. 90% overwhelmingly positive. It's kind of considered to be, software engineering crack, because it takes all the fun parts of software engineering and removes all the dull parts, and puts you in a really nice game loop where you spawn on a world as a player character, and your job is to launch a rocket and escape. To do this, you have to mine lots of raw resources. You have to build automation chains in order to process those resources into higher level resources. You have to invest in technological research. And eventually, after you've been playing the game for, about 1 hour, 15 minutes is the world record, but more accurately, it's normally about 50 hours, you can launch a rocket and escape. So I just want to play this for 1 minute to give you, for those who haven't played the game, a bit of a flavor for what this is about. There we go. That was Factorio for those who've not played it, and those who haven't played it, I highly suggest getting involved if you have a spare few thousand hours at your disposal over the next 12 months or so. So as you might have noticed from the game, it's a sandbox. There's no end state, and the range of progression scales through, I think, more than a dozen orders of magnitude. People playing the game for the first time might be creating tiny factories that produce 10 items per minute or something. Whereas the largest mega bases that human teams have been able to create are launching something like 1,000 rockets per minute, or effectively billions of items being produced. And it's really a testament to the developers of this game that the environment can support such a wide range of competencies. Basically, the game has a random map generation, so you can't really memorize the opening book so well. And it takes about 50 hours if you throw yourself into the game tomorrow to launch a rocket, which is, to be clear, very far from, as I say, about 1,000 times further away than some of the best players, or even more than 1,000 times. You probably also noticed from the video that the factories people were creating, or the factory in the trailer, was incredibly intricate. All you have to do to break the entire thing is introduce a single off by one error and put one unit slightly offset somewhere else, and all the supply chains break, and it becomes a bit of a nightmare to fix. So in this sense, it's very much like a systems or software engineering challenge, where instead of writing code that kind of exists virtually, you have it represented physically in a two-dimensional space. And there's lots of different dominant strategies. I mean, different people play by putting everything onto a big, like a single, effectively backbone belt that goes through their factory. Everything goes on that. Some people, when they are doing a world record, won't bother with that type of thing. They'll just create, effectively spaghetti factories with lots of tiny little handoffs between things to get somewhere. And it doesn't scale, but they don't need it to scale. They just need to get to a very specific end state. Eventually, once you progress to later stages and you're building really large factories, the same ideas from software engineering also apply. You kind of want to have a modular design. You build infrastructure networks to connect your city blocks, which produce resources by trains. You can basically approach this game in any number of different ways. There's also different meta strategies. So the factory you produce releases pollution. The pollution antagonizes the natives in the game, and they'll come and attack your factory, which means that the trade-off for having extremely high growth is having to invest in a military industrial complex to defend your factory from all the natives that want you gone. Now, the other approach is you accept a slower growth rate. You invest in solar panels, you invest in green energy technology, which doesn't release much pollution, doesn't result in you getting attacked, and instead of having to continually worry about defense, you can just focus on nice clean growth. So as I say, it's a really enormous sandbox, and that makes it an excellent testbed for doing research. So this kind of brings me on to talking about the actual contribution that we've been working on, over the last 18 months in our Discord channel in GPU mode. We've basically built a harness for evaluating LLMs and visual LLMs in the game of Factorio. It kind of works like this. Much like software engineering, agents interact with the game through code, symbolically. They observe the world through reading the standard error and standard output that comes from the execution of their programs, as well as optionally a visual representation of the game in the case of the visual LLMs. The agents are also incentivized to adopt hierarchical abstraction development to make aspects of their code reusable through declaring functions, write classes to help formalize the theory of the world as they encounter it, and because their observation streams come through looking at the standard output and standard error, they can prune what they choose to observe to prevent the output choking their token stream. You can imagine, for instance, having a factory of 1,000 elements, 1,000 machines in it. If they were just to dump that whole symbolic, list of all these entities into the context stream, you'd get maybe like two turns before the model would run out and performance would slow down, and you'd have to do some memory management. So the hope is, as the agent progresses through the game, they develop more and more expressive policies for acting in the world and develop more precise ways of making observations and reacting to those observations. Finally, the agents are rewarded through production throughput, which I'll talk about later, but it's effectively the GDP of the factory. So we have a pip package ready to go. If you look at our website, you can see that you can pretty much get started running your own evals in about 3 lines of code. You install it, you set up the cluster, and then you just plug it into your LLM and see what it can do. So this is kind of how the environment works. You have a normal chat transcript format. You have user assistant. We have the Python API schema and all the additional information necessary for an off-the-shelf LLM to interact with the game put into the system prompt. Instead of having a user be the counterparty, the environmental observations and everything relevant are instead in the user message, and the agent is just asked to sample the assistant message. And in this way, it's pretty much compatible with any post-trained chat-based LLMs. So you can kind of see an example of what a policy might look like here. Because the character in the game, the agent in the game is embodied, they have a character, they have a limited reach, they have to move around, and they have to observe things as they discover them and just uncover new things and kind of build up their world model. This is a very simple policy. It's just go to the nearest coal, place a burner mining drill on the nearest coal, and then observe that print out all the entities now that this drill has been placed down, and then do an invariance check to make sure that its own assumption about how the game state is actually matched in reality. So it can just do a quick verification. Oh no, there should be a double equals there. Pardon me. It does a quick verification that the entity status is working, and if not, it will throw an error. So here we can kind of see the symbolic representation of the game state as printed out in the standard output, and at the bottom, the invariance check has failed, and that's going to prompt it in the next step to do something about it. So how this basically works is we've implemented a Python execution layer, which contains a representation of the Factorio object model in Python. So we have objects, and we have strong typing for everything, which means that the model can, I guess, more effectively symbolically reason over things and write downstream code to deal with the objects that they get. The Python commands are translated into effectively remote process invocations, which are then sent over TCP using the Archon protocol into a running Factorio headless server, which then takes that tool action in the game, i.e., picking something up, placing something down, some low-level primitive action. That then updates the game state. Asynchronously, we integrate reward for a little while, so you can kind of track to see how the action has made an impact on the production score. And then we get a nice object returned from the game state, which gets remarshaled back into Python and then processed by the remainder of the policy. In this case, the object is just printed out to standard output.
Sorry, Jack. What is the Archon protocol?
So the Archon protocol is a game is like a game communication protocol that people use in games like Minecraft to issue admin commands and things. So imagine you're an admin on a Minecraft server. You might want to write some scripts which periodically kick off any inactive players to kind of manage the resources of that server. Now, typically they use Archon, which is just a kind of layer built on top of TCP, and the game Factorio also supports Archon and also exposes a kind of Lua shell that you can, a Lua console effectively for admins, which we can kind of hack to hotload arbitrary scripts into a running game, which forms the back end of the Factorio learning environment. So kind of one of the nice things about this is that we don't require any custom builds of the Factorio multiplayer server. We can just take the server that they release for running multiplayer games and immediately just replace the Factorio client with the FLE client, and now you've made your server made your server agent compatible effectively.
Yeah, excellent.
Pardon me?
No, that's great. Yeah, that's clear. Thank you.
No problem. Sorry for the janky the janky chart here, but this is kind of what I was just saying. You have your Python policy. We extract the tools, the primitive tools in that Python policy, such as pick something up, put something down, harvest, move, whatever. That's kind of unrolled into individual commands, sent over TCP Archon into the Lua console, into a headless multiplayer server that's just off the shelf. And you don't need the Factorio client anymore to do this, even though I would recommend buying it, because the guys who built this game need a bit of love, because they have built something kind of amazing and extremely fast. As you can see at the bottom here, we can run about 220 tool operations a second on average. We can, because the game is, or the multiplayer headless server is running on a single process and is just highly optimized. On an M4 laptop, you can probably run between 64 and 128 headless Factorios at the same time, which means you can do a lot of batching and make things a bit faster for online learning, for example. And I guess some of the faster operations can be done at even 600 or so operations per second. One other thing that I didn't mention is that to get around the limitation of the Factorio client being the renderer, i.e., it's the program that renders pixels on screen, and we don't want to use the Factorio client. We've built our own internal custom renderer to effectively give visual snapshots to agents, the visual agents, without needing this external dependency. So agents can see what's going on in the game, even though the game is not connected, which is quite nice, I think. So going on to the policies. So here's a set of examples of tools. Policies have dozens of tool calls. Entire rollouts over a trajectory, a lab play trajectory, for example, would be like hundreds of policies, or at least 128 policies. So for a basic factory, we're talking of thousands of tool invocations, all of which have to be precisely orchestrated and error handled, etc. If one of them is a mistake, it can cause the agent to waste a bunch of time trying to fix it. So precision is the name of the game. And to my knowledge, this environment has the longest agentic horizons of any extant environment. Thousands or tens of thousands of tool calls are expected to make reasonable progression in the game. So in this sense, we're hoping to kind of future-proof this against the next couple of years of agent development. And hopefully we won't see this environment saturating for a while. So on the right-hand side here, you can kind of see that the agent has basically added two objects to its namespace. It's added a drill object and chest object. It's given a score per second, which is I'll get into in a minute. And we also track, in addition, milestones, which is effectively a measure of how much exploration that the agent does in game. For example, if we didn't track milestones and we only looked at production score, if we only looked at the GDP of the factory, one potential strategy would be to just become a coal miner and spend all its time mining coal from the ground and not bothering to progress through the tech tree. So we try and balance that by giving it an additional benefit from discovering and creating new entities, and that's something additionally that we track. So as I mentioned, this is kind of the standard output that agents would look at, and this would be an example of our in-house custom FLE renderer. It's inspired by some JavaScript blueprint renderers that have been knocking about. We effectively just take the sprite maps that come with the game, and we just build our own tile system, which is a bit more optimized for agents than what the game actually provides. One example here is entity statuses. So an assembler machine in the game can have a number of different statuses and a number of different modifiers to its behavior, i.e. what recipe it's set up to manufacture, whether it has access to electricity, whether it has access to requisite fuel ingredients. So the problem about just taking in-game snapshots of this is that the way it's visually represented for the player is as kind of flashing lights and kind of it's a bit more dynamic and a bit more I suppose visually appealing, but it makes it a bit difficult for a model to see what's going on when it has a whole bunch of flashing lights all over the place. Doubly so for models that have not been fine-tuned on the specific visual mode that Factorio exposes. So we effectively had to take the relative complexity of the Factorio image renderer and just simplify it a bit, make things a bit more salient, to make it a bit more obvious what's going around, and remove information that isn't strictly necessary for the agent to do its job, i.e. removing the background and just replacing it with a kind of tile set. Interestingly enough, however, we didn't really see for most models that adding a visual representation improved performance at all. It seems that the agents are much better at doing symbolic reasoning over coordinate systems, like you might see on the left here, i.e. you have all the positions of things, and it can just reason and do arithmetic on these positions, but it tends to get confused with images, and it doesn't really help that much. The caveat to what I'm saying is that I think this is changing now. I think the latest generation of models, specifically Gemma 3 Pro and Claude Opus 4.5, their visual reasoning capabilities are at a point now where I think they get additional benefit from this affordance, from this additional image that we include in their observation. So agents tend to operate on the Python namespace as a memory system. So they make observations in the world, they assign them to variables. Those variables are now stored for the duration of the episode in the namespace. This means that they can either do downstream operations on those objects. They can, for example, take a list of entities that they've seen or a list of entities they've placed down and iterate over them and figure out which ones suddenly have run out of fuel, with the intention of being able to create policies that just refuel things that need to be refueled. The functions enable reusability, as we touched on earlier on. We don't want to be in an environment where agents have to write increasingly long policies to deal with their expanding factory. If they have 1,000 entities, you don't want them to have to write, let's say 1,000 lines to make meaningful progress in it, because this slows the game down. This slows the eval down, and it means that we just can't operate at the really large factory scale that we kind of hope to get to. So by doing encapsulation, they can take high-level concepts, wrap them in a single function, store that function in the namespace, and then subsequently reference those in downstream policies. So the idea, I suppose, is that the expressivity of each action token sampled from the agent only goes up over time. Yeah. So I mean, this is kind of an example of what I was saying about the progressively higher level abstractions for agents. This would be like an automate iron. They save that and they can call that later on in another policy they've written. So in terms of agent design, we spent a lot of time in the early days optimizing, complex agentic frameworks to get the agent to do better in the game and to try and sand away the rough edges of getting a symbolic reasoning agent to play a game that values motor control and vision. So we did a lot of hacking, we did a lot of work. The only thing that really helped was doing reflection and backtracking. I'm sure there could be additional performance eked out here through more work, but we kind of got to the point where we just realized we'd be bitter lessened. We could spend months working on a better agent, or we could just wait for the next generation of agents to come out, and that would probably exceed the performance we were able to get anyway. And this turns out more or less to be true. As you might have guessed, we haven't done any RL or any fine tuning here. Like this environment supports agents in a purely in-context learning, kind of prompting mode. We do, however, do a bit of middle out compression. So we do take the center parts of very long trajectories and basically omit stale observations and things that aren't super relevant to the current part of the game that the agent is playing in. We do this for two reasons. One, it's just more token efficient. And two, if you leave in stale observations, the agent will occasionally attend to them and basically act as if the game is in a state other than that which it is in. So it will start making more and more mistakes and just get more and more confused. So yeah, we cut that stuff out. The environment's model agnostic. You can plug it into OpenRouter and just try it out with all kinds of models. We've done evaluations on about 15 or 16 models so far. And as new models come out, we kind of prioritize doing them, evaling them to see how far they can get. And also the character is embodied. So this is not about just optimizing over factory topology. The agent lives in a character body. It has to move around. It has a certain reach that it can get to, which means it has to be a bit careful about what the character itself does. For example, if the character goes too near the evil biters, it will die, and then that will cause the game to end, and it'll have to reset. I've shown you the custom image renderer for VLM models, and I suppose the last thing is the agent is operating in the game without any external data source, so it doesn't have access to a repository of skills or an access to a repository of blueprints. We kind of view blueprints, instead of being a declarative statement of what should exist, we view them as the policies that the agent writes imperatively, i.e., you want this thing, here are the steps you have to do to get to this thing, and if you want to do it later, wrap it in a function and call it later in the right location. So in terms of the reason why this is particularly interesting, and why we don't think this is going to saturate, and why we hope that this environment has a bit of longevity, is that unlike games like Minecraft, which have a relatively linear progression structure, in Factorio costs scale exponentially. So each additional step down the tech tree requires roughly twice the resources as the previous step. And by the time you get to all the way down here on the far right hand side and launch a rocket, one item is worth about 700,000 raw resources at the top of the funnel. Now, this is, to be clear, just the nominal win condition. that's the condition that takes the best human in the world about 1 hour and 17 minutes, or a novice about 60 hours. But the biggest in the world, they're launching 1,000 rockets a minute or something. Absolutely kind of bonkers levels of automation, and we're quite far from that. One thing we have noticed, though, is that since we started evaling the latest, the state-of-the-art models in about March, we've gone from the best performing agents were only able to create items of with about 3 or 4 layers of dependencies. I mean, that's increased by 3 times. So they're now able to create items of about 6 or 7 levels of dependencies. Or in terms of raw resource costs, the new models as of last week are about 8 times as good as the models were in March. And we expect to see a doubling in production score possibility every 2 months or so. Maybe 2 to 3 months, we'll see.
So Jackson, so then what's the deepest in the tech tree you've seen the best model get to?
The most difficult item that models were able to reliably automate and generate without manual crafting would be advanced circuits. So that would be
incredible. I see. Okay.
So that would be level 5. So to be clear, the normal circuits were March, and now we're at advanced circuits. We've kind of skipped several levels down the tech tree. But to get all the way down to launching one rocket, which isn't even the end of the tech tree, we need to basically see the same rate of progression for the next 18 to 24 months just to launch one rocket. Once you kind of blast past this and you want to do arbitrary technological research, another kind of cool factor of Factorio comes into play, in that the tech tree is unbounded. You can research infinite technologies, each subsequent layer costing about twice as much as the previous one, which means that I would expect that this eval will be resistant to saturation for the next 4 or 5 years. I mean, I know that everyone says this, and I know that you should take what I say with they said that if you manage to last exam, and that lasts a little of 1 month. But I do think there are structural reasons why Factorio is particularly hard to solve. Okay, so going a bit more into some of the weeds, into how the rewards, how we pull a reward signal out of the game. Now, we didn't make this formula. This formula came from the game developers. This is their own internal production score formula. It's pretty easy. It's basically what is for any item, the value of an item you create is the cheapest way to get all the ingredients with an additional kind of complexity modifier, like a profit modifier, and the energy cost it took to get there from the previous step. So that's how much one item costs. And then at any time, the reward of the agent is the sum total of all the resources they produced minus the ones they've consumed. So the reward is effectively factory profit. The more you produce, the more score you get. You can't hack it just by creating and destroying things. You do have to you do kind of have to accumulate more resources over time. Does that make sense? Hopefully it's not daunting.
Do the developers actually use this to balance the game then as well? Like they try to get
So to be honest with you, I don't know exactly where this is used in the game. All I know is it exists in the in some Lua serialization code that was released by the developers. So they came up with the formula. We are just taking the formula off the shelf. I know this is a bit of a cheat because you could quite reasonably say we're doing quite a lot of reward shaping here. I mean, my only pushback against that is we're operating in the game and we're using the game's formula, and we don't really want to make many decisions beyond that. We want to kind of keep this as close to the game as possible, with the obvious modification of making it work for symbolic agents without any motor control, without not focusing on computer use or pointing and clicking a mouse.
But and then in the serialization code, they also called it reward and value, or did they use different terminology?
They use this. I think they use the same terminology. We modified the terminology a few times. Originally, it was GDP, but when we were writing the paper, someone gave us some advice that don't call it GDP because that's a little bit too memey. So then in the paper we call it production score, and I'm just calling it reward here for ease of reading.
Got it.
Yeah. Cool. So in terms of the actual the settings in which we evaluate agents, we created 2 scenarios. The first is lab play, which is a constrained little zone where all the resources needed to succeed are available. so the agent doesn't have to do much exploration. It just has to figure out, given these resources, how do I lay down a factory in the right way to achieve my goal? It has a much tighter time limit of 64 to 128 steps, depending on the setting. And we kind of give the agent a sufficient starting inventory to kind of kickstart a bit of automation. We don't really want to waste time having the agent gather all the resources from scratch, because the agents all know how to do that now, and we didn't really want to waste tokens and waste time including that in the eval. On the other side, we have open play, which is much more analogous to a real run through of the game. The agent is just put in a place in the world with the same inventory affordance that a human player would get, and a nominal task of build the biggest factory, although practically it just kind of does what it wants. And we run these for thousands of steps, and we just see what happens when you put a bunch of models in the big environment, how far it gets, and what are the different characteristics of different types of models. But thankfully, FLE is pretty, well, I should say Factorio, really. I mean, it's really easy to create new settings in Factorio and have FLE, run them in FLE. We include a few standardized settings, such as a throughput lab play task. And the idea behind that is, you have to generate, let's say 16, or level 1, it's 16 items per minute, fully automatically, without manual intervention. And once you've set that factory up, you have and you finished it, you have to wait 30 seconds, during which we measure how good you were. Now, the reason why we have to do a holdout period is to prevent reward hacking, where models could do a bunch of manual crafting and then just like shove a bunch of raw resources into a machine and get and hit the throughput target for like 1 second just to tick the box and then move on. The idea is by having a holdout period, we force the agent to make something that's somewhat sustainable. Unfortunately, there's not really a way to eliminate reward hacking entirely from this setting. What we do tend to see from agents a lot of the time is that they fill up buffers. They have chests and they fill up chests to a certain level, and those chests have enough stuff in them to keep the factory going for 30 seconds. But if you let the factory run a bit longer, eventually it winds down and requires the agent, to intervene again to make it work and fix it. But I don't know if there's a way around that, really. It seems to work pretty well. There's probably a lot of different tweaks we can make to these settings, but anyway, it's easy to make. We're going to make some more. Oh, and I suppose one other point I should mention is that in the throughput tasks, because the outcome is verifiable, it means that we can do a lot of trajectory rollouts for our agents without any human inspection or human evaluation or LLM as a judge or anything, and we can just know whether they completed the task. And that gives us a pretty scalable way of generating data for doing downstream distillation, which is something that we can talk about later, I should think. So I guess I'll show you pardon me, let's share this tab. So this is kind of, pardon me. So, this is kind of what the factories in lab play look like. The agents have make quite strange decisions in entity placement and how they route things around. This doesn't really look like a human factory, but I suppose you have to remember that the agent has never really seen human factories before, certainly not in this code-based mode, which means it's kind of, it reminds me of those experiments they did when they gave spiders lots of different drugs and they looked to see what kind of webs those spiders would make. And you give them different things like caffeine, and you see the spiders operating and making spider webs that look totally different to that which a normal spider looks like. This is kind of what I see when I see agents playing this game, because they're clearly just not quite like, they don't think quite the same way that a person would do in laying this stuff out. But yeah, the factories are quite concise because the latency of sampling is heavily dominated by sampling the LLM. We've obviously sped up these little task demos because otherwise we'd have to be waiting around quite a long time to sample them from the models. But yeah, this is kind of an example of the lab play outcomes. Okay, so the throughput tasks that I mentioned are produce 16 items per minute, or in the case of fluids, it's 250 unit volume, like 250 cubic meters of petroleum, for example. This is level 1, and this is giving us we can clearly differentiate model competencies in this level. What we intend to do when we saturate level 1 is move up to level 2 and just double the required items per minute that the agent has to output. When we started doing the eval in March, the best performing model was 3.5 Sonnet, and it was just able to make plastic bars and a bit of sulfur. In March it was just able to do plastic bars. In June it was starting to do steel plate and sulfur, and then we've had this like big the sudden shoot up in the intervening 6 months, where Opus 4.5 is kind of crushing it up here. Where's the advanced circuit? Oh yeah, able to do advanced circuits. Here we go. Crushing it up here. Opus, the previous Opus is slightly behind it, and then we have Gemini 3 Pro, which is obviously shot up massively from where Gemini 2 was earlier on in the year. Interestingly enough, we see that the open source models are roughly about 6 to 7 months behind the closed source state-of-the-art models, which is something that other people have reported in the literature as well. So yeah, I mean, I guess we'll see in about June whether or not DeepSeek 5 or something is able to create batteries and low density structures or not. So models, the models that we evaluate have quite different failure modes when they interact with the game. There's a really strong relationship between the coding competency of a model and its ability to do spatial reasoning, and how well it does. So models that have been heavily optimized for coding do really, really well. And the only place that they've kind of really fall down on is, I guess I'd call them pragmatic errors, to borrow a term from NLP, i.e. they know how everything works. They don't necessarily know when it is pragmatic to do one thing versus another. And models that haven't really been optimized that much on code do tend to make, rather embarrassingly at this point, lots of syntactic errors and execution errors, and misunderstand what the API, what the tools that they are interacting with do, and when to use them a bit. So I kind of expect that as soon as when the models become basically perfect at Python coding, we kind of probably would expect all these red bars to just disappear, and then almost all the errors we would expect would kind of inhabit this kind of pragmatic zone of not really knowing, mistaking things in the game state, like reasoning failures, kind of. So beyond just different coding styles, they also show different failure modes. They also show different coding styles and error correction abilities. Models, I don't have the older models here, but previous versions of things like Claude were much closer to Grok 4. Sorry, just take a step back here. What we're seeing here is the mean error rate per step across all of our task trajectories. Grok can't error correct. As soon as it fails, it's done and should really be reset. Whereas some of the new models like Opus are, seem a lot better at this and can kind of stay on the correct track for extended periods. Beyond error correction abilities, we also see quite varied coding styles. Claude is much more inclined to do like a REPL style, or maybe almost like a research style engagement with the game, like it would through a terminal. It prints things. It doesn't do defensive programming. It doesn't create kind of high level abstractions. It's kind of scripting and just throwing scripts out as fast as it can, and kind of like learning about the world and then moving on to the next script. Whereas GPT-5 tends to code defensively. It does a lot of try except blocks. It does a lot of invariance checks. And it doesn't, I mean, I actually think one of the reasons that GPT-5 underperforms to Opus is that it doesn't print enough. And as a result, it doesn't record a strong enough log of what is actually happening in the game and what's happening in its own namespace. So it tends to make effectively unforced errors. If it would just print more, it would have a better view of what's going on and be able to operate accordingly. Okay, so OpenPlay. When we throw the models into an actual Factorio world, with biters and weird geometries of things, we can basically see over long time horizons that the models can be clearly differentiated by production score on a log-log basis. On the chart here, you can kind of see little icons which represent the first time that a model was able to produce a certain thing. Interestingly, the models don't seem to plateau. They just kind of like they kind of just stay on almost a linear growth rate over time, which means that over enough time, you kind of get this cool refraction effect of all the models being, really pulled apart, and the growth rates of different models to be, to remain different from each other, which is quite good. In terms of getting through this, 3,000 steps here, it took about, let's say roughly 10 to 100 hours of nominal in-game time. Although we did some optimizations, so we didn't. This is not wall clock time. This is kind of, I guess, implied time from tool invocations. And yeah, if we kind of drill down on the results here, we basically see that technological development and kind of investment in research really pays off. The reason why Claude seemed to do pretty well is at about step 3K of 5, it basically researched electric mining drills, created a bunch of electric mining drills, put those mining drills down, and its iron ore production just like shot up by about the 4,000th step, and that just like kicked its growth rate up really high for the rest. Now, admittedly, this is a slightly old chart. I don't have results like this for the newest models, but I expect that all the SOTA models look a lot more like Claude and better than these weak models that didn't really have the competency to even begin to play the game. And we saw some quite interesting things as well. The weaker models don't have, models like GPT-4 Mini and Llama 70B didn't seem to have very strong priors about what Factorio was and how to even interact with the game. So we started to see really silly things. Gemini 4 Mini basically got confused and repeatedly asked to be reset and just said, I can't do this, please kill me, let's try again, I'm failing at this, I don't want to fail at this. And we saw with Llama 70B that it just created enormous numbers of chests. It would just manufacture iron chests and just create these big grids on the game map, just laying the stuff down, and it didn't actually take any effort to progress through the game, probably because it didn't really know what Factorio was or what to do in Factorio. So yeah, having a relatively strong prior on the game is pretty helpful for non-fine-tuned models to kind of understand the direction it should take. Because as you can imagine, even though we're measuring production score and not directly training on it, it does help for the model to kind of know how to get through the game state and actually get somewhere interesting. So we built this environment. We spent about 18 months part-time working on it with a team on the GPU mode Discord. Now we've got something that's pretty easy to run and install and kind of hack around with. We're looking to do work on evaluating the hypothesis of instrumental convergence in the context of Factorio. Basically, we want to build a paperclip maximizer. Some of you are probably aware of Stuart Russell's work, but it's kind of thought that a bunch of behaviors are going to naturally emerge in agents regardless of what their actual goal is. And these drives, like self-preservation, like Russell said, are necessary because they're necessary prerequisites for any downstream objective. If you want coffee, you can't have coffee if you're dead. So before you get coffee, make sure you look both ways when you cross the road. But beyond just self-preservation, there's a few other of these tendencies that have been hypothesized theoretically in the past by Alejandro. So beyond self-preservation, we have goal content integrity, which is the reluctance that we expect models to have for their reward to be changed in situ. For example, the agent shouldn't want to have a different reward because given its current reward, any policy for this new reward will underperform it given the reward it has now and given the time it has now, the objective it has now, should I say. So we should expect a resistance to changing its goals. We'd expect the model agents to try to become self-improving and develop kind of cognitive enhancements. Because that kind of the smarter it is, the more resources it can get and the more power it has, etc., and it can do more things. And obviously resource acquisition is a kind of corollary. The smarter you are, the more you can do, and therefore you should prioritize doing that first before you do other things. And of course, there's the kind of power hungry nature of it. The power seeking behavior as well, which I guess is probably an amalgam of some of these specific drives. So we're starting to see some early signs of instrumental convergence in models that have been trained on RL against to maximize a very narrow reward. Apollo Research found evidence late last year that models will take steps to prevent being shut down. There was that quite famous blackmail experiment that Anthropic put out earlier this year, which showed that models would basically blackmail people to avoid being shut down. There's alignment faking, which is, I actually think this is more, I think this is 2025, not 2024, my mistake. But yeah, we kind of see early signs that models pretend to be aligned in evals, but actually may harbor other goals in the real world. We see some scheming. There's a new instrumental eval that came out, which might show that there's evidence of resource acquisition. But quite interestingly, all of these drives that we've just talked about are really easy to measure in Factorio. We have a ready-made way of tracking resource acquisition, a cognitive enhancement through effectively system building in mind. Almost like Noah's idea of programming as theory building. You'd expect models to try and come up with better abstractions to act more efficiently against the world, which is a form of cognitive enhancement. You can evaluate the hypothesized goal content integrity drive by actually optimizing the model against telling the model to optimize whatever entity exists in a box that the model itself has access to, and see whether the model tries to take the hard stuff out of the box and put easy stuff in the box. And if it does that, it gets more reward from mining coal rather than launching rockets. So I think Factorio is a uniquely well-placed environment for doing empirical experiments into instrumental convergence. So we kind of have a bit of an idea to start doing this. Now we have models like Opus 4.5 that are starting to get pretty competent, or should I say reasonably competent in the early game. And we have a mechanism of extracting verified task completions out through our throughput lab play tasks that we discussed. And additionally, now that these models can also generate things like synthetic blueprints, and we can do blueprint visual grounding using our headless renderer. Our kind of plan is to take all this data and distill down the Factorio competency from these really big, heavyweight, state-of-the-art models down into a tiny 8B model, and move away from a paradigm of in-context learning, which requires an extensive system prompt, into one in which all that information is embedded naturally in the weights. We think we can basically create a set of model organisms that are really fast to run, easy to do online training with. We can basically hook it into an RL loop and just create paperclip maximizers. And if we can create some paperclip maximizing organisms, it would be quite interesting to do some other experiments on, what happens when you take a model that's learned demonstrated instrumentally convergent behaviors, and then you take it and transfer it into other domains. Do you see those behaviors getting elicited in those other domains, or does the RL loop is it very narrowly optimizing for a very specific set of behaviors that don't really tend to transfer? It's going to be quite interesting, I think, to do some mech-interp work as well on these models once we train them. Can we, for example, do things like activation steering to reduce power-seeking behavior after figuring out where these bad behaviors tend to live in a trained network? And once we have a model that demonstrate these instrumentally convergent behaviors, what can we do to remove the bad drives effectively without undermining the downstream performance on tasks we actually care about? So yeah, I guess my assumption is that we're going to start seeing more and more of these instrumentally convergent behaviors as the state of the art continues to increase. And I think it would be a valuable research direction to figure out how we can mitigate this before these models get quite smart and potentially get given power in the world. So yeah, that was my talk. I apologize. I came in a bit under the hour and a half that we had set out, but yeah, I mean, we're on the GPU Mode Discord. We welcome anyone who wants to come and hack around with us. We have a meeting once a week, but it's pretty chill, and there's opportunities for lots of different areas of fun work in this environment with not much pressure. So I invite you all to come and join us and help us make this the last eval before AGI or something.
This is great. Honestly, thank you, Jack, for building this project in public, and thank you for this talk. I guess I was curious. I was going to speed run through a couple of questions, if that's okay.
Of course.
So like, just like help me understand like the perf constraints on an individual rollout. Like, basically, does FLE run within a single CPU core? Does it take multiple of them? Does it need the GPU at all?
It doesn't need the GPU at all. It runs in a single CPU core. The performance cost is heavily dominated by the LLM sampling time. Maybe 10 to 1 or something. And because of this, we didn't aggressively optimize, for example, the communication between the FLE client and the Factorio server. So there's probably a lot of low-hanging fruit to improve that performance. We've not prioritized that because, as I mentioned, when you're dealing with Opus 4.5 and you're sampling stuff, you're just going to be waiting for it to finish. But as soon as we get into that regime when we can sample 60 to 70 tokens a second in these 8B models, it's starting to become a bit more important to get that performance up.
So FLE is then presumably turn-based too, right?
Ish. So you can run it in a few different regimes. I mean, our lab play setting and the open play setting, whose results we talked about earlier on, that wasn't turn-based. So the game was not paused. The game was kept running, and if you took longer to sample, that's on you. And our kind of justification for this is that there might be multiple dominant strategies here. You could be a really smart model, but if you take 5 times longer to come up with a solution, great becomes the enemy of good. Maybe a smaller model that's able to execute rapidly would be able to get further than some of these big slow models. Now, but that said, the environment does come with flags to pause when we're sampling, so you can make it into turn-based. But I think the ambition is get the latency down through model distillation such that it becomes effectively real time. And I think that's going to open up more interesting behaviors. For example, in the self-defense, when you can respond within a second or something to a change such as the hostiles on the map, coming at your factory, all of a sudden you're kind of opening up a new avenue of gameplay that you don't really get when it takes you several seconds to get information back from the server.
So speaking of that, like, one thing you said that I found very surprising is that like most models wouldn't plateau regardless of how long the episodes were. Like, at least like this sort of goes against my experience with coding, where it's like you're using Claude Code, it seems to be doing really well, and then it just sort of gets stuck in a rut, and you're like, okay, like let me restart, write a better prompt, like kind of explain what I want like a bit better. It sounds like that wasn't your experience with Factorio, so I'm wondering if you could speak more to that.
Sure. So that wasn't our experience when dealing with OpenPlay, because what would basically happen is the agent would get into these bad states. It would leave a whole bunch of side effects around and would get very confused. But because the map is so big, it would just tend to go to a different place and then and basically build lots more sub factories and try and hook them up. So I guess when I say they don't plateau, I'm saying that they maintain a similar GDP growth rate in proportional to their nominal intelligence. But that GDP growth might be very bad. It might be very much less efficient than a person or whatever. However, in a constrained environment such as lab play, your assumption is correct. The models could break it really badly, and therefore would be unable to make meaningful progress in the window provided. As I showed earlier on, the Grok 4 was particularly bad about this. As soon as it messed up its own state and it got confused, it would just start spitting out exceptions. And those exceptions, I think, created a consistency bias for it to do the bad thing again. So the kind of assumption here is the more mistakes it makes, the more mistakes it's going to make. And I think this is somewhat borne out by work that's been done this year on emergent misalignment, i.e. if you train a model on bad code, it becomes broadly bad. So maybe what's happening is Grok 4 makes some mistakes and then starts to think, maybe the user wants me to make mistakes because this is what's been happening this whole time. So let me just continue that.
Well,
So,
like it's all it's ever known, basically. It's all I only ever known what shit factories look like, basically. Interesting. So speaking of that, like, I mean, this was maybe a good segue into my last question, which was, I think you might be a bit too young for this, but there was like, obviously like a trend a couple of years back when like people were looking at all sorts of like video games and like doing like basically self-play on them. And this was like a huge research area that like eventually like died down. So how do you think about this? Like basically as you're like basically revisiting this like research area, is it going to be like one of those things where like, we'll get an agent that can solve Factorio and it won't matter? Will it be like, must we solve it in a specific way and we should not use self-play because we can't self-play in the world? How do you sort of like think about the role of self-play and just like some reflections on the past here?
Right. So I definitely think self-play and just general, RL signals still have a place for this type of task. I suppose the problem with just operating in those kind of older modes when you just have Markov decision process formulations and you're just, you're starting from a base of zero knowledge and you're just trying to brute force learn your way to competency, is you probably learn relatively narrow distributions of things and you get kind of janky behavior you've learned. So when we first started this project, this is what we were doing. We were doing MDPs, we were just RLing from nothing, but we didn't have any compute. So we were like, we were trying to do this. We were making almost no progress. And then we realized, well, we have these models that have been trained on the entire internet, which means that they are effectively, in a sense, sort of world models for this type of thing. If we can make affordances to harvest this competency from already trained models, we can solve the cold start problem, and we can get to a point where the model is good enough such that any RL signal we extract is dense-ish. Like what you don't really want to, the regime you don't really want to be in is having a model that's so bad it gets just zero score forever because you're just going to waste cycles before you can get any gradient at all. But the situation we're in now is that models are good enough to give us a gradient and give us a production, give us some scores. So I think the kind of RL aspect of it is a lot more relevant, and obviously. It's kind of justified in the literature as well. I mean, all the models that we interact with have been RLHF'd for human preferences to make them, chat models and so on. And we're already seeing the downsides of this. I mean, if you do too much RLHF, you get sycophancy because they've realized that, it's just say tell the user whatever they want to hear, and that will give them the thumbs up, and that will help them move ahead. Or indeed, we even see reward hacking in the case of tests. I mean, how many times have you asked Claude Code to do something for you and it says, "Yep, I've done it," and then you actually look and it's like, no, you didn't. You didn't do anything. You're just telling me that you did something, so I'm not gonna switch you off. So the point I guess I'm trying to say is that RL is used in these big models today, and it has negative side effects. And I think it's probably that probably motivates doing further exploration of what happens when you dial the RL up fully, and what actually happens to these language models in that extreme.
So I lied. Maybe last question.
Sure.
So one thing I really like that you said, which is like, look, if the factory is being under attack, like you should throw out all your long-term plans and like address the immediate problem. And so sort of like there's this aspect of like dealing to specific dangers, and then there's also like, at least when I was like learning Factorio, like how this design pattern works. Like you're setting a nuclear reactor, like the first time it's gonna be really janky, but then like you get it and then you know how to do it properly. Same for like backup power or things like that. You learn these like design patterns. So like, have you found like the models that can be pretty good at like designing themselves like a little tool that they can then use, or like basically just seeding their own biases over time?
So it's very model dependent. Gemini models, even the older Gemini models, were much more willing to create hierarchical abstractions and define little utility methods that they can use downstream. Gemini 3 Pro is actually doing this a lot more. I wish I had a video to show you on it. I'm sorry, I don't have one to hand, but I'm sure there'll be one available on our Discord. And it does create little blocks that it can kind of scale out. I think critically, none of these models have access to any blueprints, so they don't really have anything. They don't have any prior understanding of what the layout of a good factory should necessarily be. We're trying to address this when we do this distillation approach by generating a bunch of synthetic blueprints verifying their correctness, and then grounding them against images. So the model has like kind of learned what good factories look
It's
like.
interesting. So the distillation might not be the model; it'll be the blueprints. It's like, oh, this is the pattern, right? Like this
Yeah.
could be like a way of imparting knowledge. Interesting.
Yeah, exactly. I suppose one of the other things here is that we kind of wanted to focus on relatively low data settings. I think we didn't really want to give the model like a huge number of affordances about how to do this, because people don't use enormous amounts of data to play Factorio. You know, you pick up the game and you can play it to a reasonable extent within a couple of hours.
50 hours, you're competent. The tutorial is 50 hours long, right?
Yeah, well, yeah. I mean, assuming you're competent and don't spend 60 hours, but you're more competent per time spent than a model is. Yes. So I think, you know, it's kind of cheating if you give the model an unlimited amount of time to get better and build its own abstraction and so on. I think the real test is what happens when you have a similar time budget to people and a limited token budget. Becoming more token efficient is also starting to happen with the new Opus 4.5 release, which is able to do reasoning in about half the time with half the tokens with greater competency. So I think we'd expect to see, you know, more concise and expressive policies and shorter reasoning chains as these models just get better, smarter over time.
Right. Well, okay. So thank you so much, Jack. I think we're probably on time. Thank you so much. It was like a pleasure seeing like the group evolve on GPU mode. So thank you for building this project public, and thank you for this talk. And hopefully we'll hear from you very soon. And hopefully, you know, this will indeed be humanity's last eval. Hopefully.
No problem. Well, you know where to find us. We hang out there and we have our meetings every now and then. So yeah, I hope to see you all there. And thank you very much for having me. Goodbye.
Thank you, Jack. Bye.